Welcome to the topic on numericals on a beam using a beam stiffness matrix. My name is Muttanna Bandar, SG Balekondra Institute of Technology, Belgavi. Before going to the numericals, let us discuss what was been discussed in the previous two sessions. So let us recall, we have discussed about the beam stiffness matrix, which is given by E into I divided by L raised to cube into the 4 by 4 matrix. And also we have discussed about the Hermite safe functions. So those two equations like a Hermite safe functions and a beam stiffness matrix both will be used in this numericals to calculate what is the deflection of a beam. To start with, we have to write a basic equilibrium equation which is written as F is equal to K into U, where F is nothing but a load vector, K is a beam stiffness matrix, and U is nothing but a displacement vector. And this F is nothing but a load vector which is nothing but a shear force and moment at node 1, shear force and moment at node 2. And these will be unknown terms which will be given by some empirical formulas. So depending upon the beam loading condition, whether it is a uniformly distributed load or a point load, these empirical formulas will be different, and that will be given at the time of solving the problem. And this stiffness matrix, wherein E, I and L will be the given conditions for a beam, and based on those things we will be calculating a stiffness matrix which will give the stiffness behavior of a structure. And the load vector which we have to find, like v1 is a vertical displacement in at a node 1, theta 1 is the angular displacement at node 1, v2 is the vertical displacement at node 2, and theta 2 is a angular displacement at a node 2. Suppose if we take this as a beam, node 1 and node 2, so these are the unknown terms, so that we have to find. So briefing about this, we'll go back to the numericals. So let us discuss a simple problem wherein I have considered a one beam whose length is L is equal to 1 meter. So these are the given term. And similarly, it is subjected to a uniformly distributed load of 12 kilonewton per meter. And this is a uniformly distributed load. And also he has given the given data like Young's modulus of the structure is 200 gigapascal, and moment of inertia I as given as 2 into 10 raised to 6 mm raised to 4. So with these given data, we will be solving the problem. To, to start with, let me write a equilibrium equation. F is equal to K into U, and F, the structure is discretized as a one element, so I will take this as a node 1 and this as a node 2. So hence I have a four quantities like F1 and M1 at node 1, F2 and M2 at a node 2. So V1 and V2 at are a vertical displacement at node 1 and node 2. Theta 1 and theta 2 are the vertical displacement at angular displacement at node 1 and node 2. Now we have to find the stiffness matrix, that is K is a unknown. So for that, let us calculate it. So before calculating it, we have to take care of the unit consistency, because moment of inertia is in terms of mm raised to 4, and load is in terms of a kilonewton. So let me convert, have a common a unit consistency. For that, L is equal to 1 meter, E is equal to 200 gigapascal, that is converted into kilonewton per meter square, which will be 2 into 10 raised to 8 kilonewton per meter square, and I is in terms of meters, it will be 2 into 10 raised to minus 6 meter raised to 4. So with this, I will calculate this term first. E into I divided by L cube. E is equal to 2 into 10 raised to 8, and I is 2 into 10 raised to minus 6. L is equal to 1 meter, so it is L cube. So on a simplification, I will get around 400. So next, we have to calculate a element stiffness matrix for the element 1. Since we have considered only one element, so the stiffness matrix will be only K1. So the formula for that is given by Ke is equal to E by L cube into 4 by 4 matrix, and also we have to write the corresponding parameters like displacement parameters to the corresponding rows and the columns. So I will renumber it as V1 theta 1, V2 theta 2, and similarly the row wise I will write it as V1 theta 1, V2 theta 2. So writing this will help you to while assembling the global stiffness matrix. Suppose if we have a two elements, then I will have a two stiffness matrices. So while assembling those stiffness matrices, so this numbering, like numbering of the columns and the rows, will be very useful. So we will discuss this in a next problem. So idea is we have to number the rows and columns as per their degrees of freedom. So once that is done, so E into I by L cube is given as 400. I will substitute here, and since L is equal to 1 meter, so wherever L is there you substitute it as a 1. So 6 into 1 is 6, 12 as it is, 6 into 1 6, and 6L again 6, 4L square is there. So L square 1 square will be equal to 1 square. So 4 into 1 is 4. So substituting the L in this equation, I'll be getting this stiffness matrix. And remember to write the degrees of freedom to the corresponding rows and the columns. Okay. So with this, let us substitute that stiffness matrix into equilibrium equation. So already we have discussed about the nodal displacement vector and force displacement vector. Force load vector. So load vector is given as F is equal to F1, M1, F2, M2. Shear force, moment, shear force, moment at each of those nodes. And this load vector, as I discussed previously, they will be having some empirical formulas, and wherein F1 is given by P naught into LE by 2. This is a shear force at node 1. And M1 is equal to P naught L square E by L square by 12. It is a moment at a node 1. And this shear force is a load at a node 2, and this moment is a moment at a node 2. And you note that the moments will be one will be clockwise and anti-clockwise. Because of that, there is a sign convention change in the signs. This is positive and this is negative. And since the vertical force will be acting in both are acting in a opposite direction, in the same direction, so they carry the positive value. Now upon I have to substitute this load vector, calculate this load vector. So that load vector can be calculated by substituting a L and a P. So hence P naught is 12, L is 1, so it becomes 12 into 1 divided by 2. So that is equal to 6. Since P naught it is acting in a downward direction, I will give it as a minus. So it is minus 6. Similarly, the moment at node 1 is given by 12. So it is acting downward, into L square is 1 square divided by 12. So that is equal to minus 1. So similarly, the shear force at node 2 will be the same, and shear force moment at a node 2 will be positive 1 because it is carrying a negative here. So it becomes minus of minus 12 into 1 square divided by 12. So it carries a positive value. So after calculating this load vector, I have to substitute all the things into an equilibrium equation. So to understand the boundary conditions, I have to go back to the boundary conditions of this. So here the boundary conditions, when I say if it is hash, the rotation as well as the displacement is arrested, in the sense v1 is equal to 0, theta 1 it is not allowed to rotate, so hence it becomes a 0. And since here a roller kind of boundary condition is allowed, so hence v2 is equal to 0 because it is not allowed to move in a vertical direction. So v2 is equal to 0. But since the roller is there, it will try to, the beam will try to rotate like this. So hence there is a occurrence of this theta 2. So theta 2 will not be equal to a 0. So we should understand these boundary conditions and substitute those boundary conditions back into this nodal displacement vector. So let us do that. So k I have substituted. So this k is from this equation, and v1 theta 1, v2 theta 2, and this load vector is from this f. So I'll go back. Now since from the boundary conditions v1 is equal to 0, theta 1 is equal to 0, v2 is equal to 0, and theta 2 is unknown. So this we have discussed from the boundary conditions, right? So once this is done, wherever the uh, nodal displacement factors are 0, those rows will be cancelled. So I will cancel this one because v1 was equal to 0. So I will cancel this row because theta 1 was 0. So I will cancel this row because v2 was 0. Correspondingly, I will cancel the corresponding columns. So since row 1 was cancelled, I will cancel column 1. Row 2 is cancelled, column 2 is cancelled. Row 3 is cancelled, I will cancel column 3. So the leftover will be this 400 into 4 into theta 2 is equal to 1. So this, using this, we will calculate what is called as theta 2. So these boundary conditions already we have discussed. So theta 1, v1 and theta 1 are 0 at a node 1 because it is fixed. theta 2 is not equal to 0 because as the node is 2 is allowed to rotate. So because of these boundary conditions, those rows and columns got cancelled, and using this relation I will calculate what is the theta 2. So theta 2 is equal to 6.25 into 10 raised to minus 4 radians. Now the nodal displacement vector will be 0, 0, 0 and 6.25 into 10 raised to minus 4 radians. So I will use this load vector to calculate what is the maximum deflection at the center. Suppose if I take this as a beam, so now based on the nodal vector, so it is 0, theta and v1 are 0 at node 1, and slowly it will try to bend like this, and here there is a theta 2. Now I have to calculate what is the deflection at the center. So when it is a center, I have to substitute what is the local coordinate of this, that is zeta is equal to 0. So in the Hermite functions I will be substituting this, and I'll get what is the maximum deflection at the center. So for that, let us consider v is equal to the function of nodal displacement vector and Hermite functions. So wherever the nodal displacements are 0, you cancel those. So v1 was 0, this terms goes off. Theta 1 was 0, so this term goes off. v2 was 0, so this terms is also 0. So since this theta 2 is equal to 6.25 into 10 raised to minus 4 radians, so I will be using only this equation now. So applying the boundary conditions, I got this V maximum is equal to L by 2 H4 into theta 4, and H4 is nothing but a Hermite functions, which is given by minus 1 minus zeta plus zeta square plus zeta raised to cube by 4. So I will substitute this here, LE by 2, so L is equal to 1 by 2. So at the center of the beam, zeta is equal to 0. So I will substitute zeta is 0 in this equation. So this is 0, this is also 0, this is also 0. So leftover is minus 1 by 4. So and theta 2 is given by this. So 1 by 2 into minus 1 by 4 into 6.25 into 10 raised to minus 4. So upon uh, simplification, I get what is the maximum displacement at the center of the beam. So which is given by 7.8125 into 10 raised to minus 5 meters. So with this, we complete a problem 1. So we'll discuss about a next problem. So here slightly a complexity is increased by adding a one more element. So the structure is of a 2-meter length, and at one end it is fixed, and at the mid of the beam there is a roller support, and at the extreme end of the beam it is again a roller support. So now we should be able to make out the boundary conditions. So let us do that here before going for the discussion on the problem. So if it is fixed, so v1 equal to 0 here, theta 1 is equal to 0 because it is not allowed. But here v2 equal to 0 and theta 2 is not equal to 0 because it is allowed, a rotation is allowed here. The boundary conditions is a rotation here. So theta 2 is not equal to 0. And here v3 is equal to 0, theta 3 is equal to 0. Sorry, is not equal to 0 because I have to find because the rotation is allowed here. So these are the boundary conditions that we will be taking into a later stage. And coming to the problem, so I have to solve for the vertical deflection and the slopes at the point 2 and 3. Point 2 is this, point 3 is this. At point 2 and 3, using a beam elements for a structure shown in a figure. Also determine the deflection at the center of the portion of the beam carrying a in UDL, uniformly distributed load. In the sense, I have to find what is the deflection at this point. So where it is carrying a UDL. And again the parameters are, he has given Young's modulus as 200 gigapascal, moment of inertia as 4 into 10 raised to 6 mm. Also we have to take note of unit consistency. This is in meters and this is in mm. Convert this into meters, and similarly the load vector is in a kilonewton per meter. So I have to convert this gigapascal into kilonewton per meter square. So with this, so this is the idealization of the beam structure. So since there are two elements, so I am marking this as element 1, this is element 2, and degrees of freedom are V1 and theta 1 at node 1, V2 and theta 2 at node 2, V3 and theta 3 at node 3, and similarly the load vector will be F1 shear force, moment M1 at node 1, F2 and M2 are the load vectors at node 2, F3 and M3 are the load vectors at a node 3. So in the sense it becomes a 6 by 6 stiffness matrix because there are 6 variables, 6 degrees of freedom, V1, V2, V3, theta 1, theta 2, theta 3. So in the sense the stiffness matrix will be a 6 by 6 matrix. So as I told, we will maintain the unit consistency, that is kilonewton and meter. So L1 is 1 meter, L2 is 1 meter, E is equal to 200 gigapascal, that is equal to 2 into 10 raised to 8 kilonewton per meter square. I is equal to 4 into 10 raised to 6 mm raised to 4 equals to m into 4 into 10 raised to minus 6 meter raised to 4. So I'll calculate E into I by L cube. Upon simplification, I will get 800. So once this is done, let's substitute that in a stiffness matrix. So this is the equilibrium equation, and F is a load vector, K is a stiffness matrix, V is a displacement matrix. So this is only for the one element, but since I have a two element, there are 6 nodal load vectors, load parameters, and 6 displacement parameters, and 6 by 6 stiffness matrix. So let us calculate the stiffness matrix for the element 1. So the length of the element 1 is L1 is equal to 1 meter. I will substitute wherever the L is there, I will substitute that with a 1, and EI by L cube is already calculated, so I'll write that as a 800, and don't forget to write these degrees of freedom parameters for the corresponding rows and the columns. And I told this will be useful while assembling the global stiffness matrix. And also remember that V2 and theta 2 is a common node that will be sharing. This will be common to this element and this element. So the assembly, the connectivity will be there between element 1 and element 2. So it becomes very important to understand to write this nodal parameters. Okay, so now for the element 2, everything remains same because element 2 length of the element 2 is also 1, and EI by L cube is 800. I'll keep as it is. The only difference is these terms. Now they become V2 theta 2, V3 theta 3, V2 theta 2 and V3 theta 3. And you note from K1 they are different. This is V1 theta 1, V2 theta 2, V1 theta 1, V2 theta 2. So hope you have noted these variables carefully, because this will be useful while assembling. So let's go for assembling of the stiffness matrix. Now global stiffness matrix Kg is given by K1 plus K2. So for that I will write first V1 theta 1, V2 theta 2, V3 theta 3, V1 theta 1, V2 theta 2, V3 theta 3. And since 800 is common, I'll take it as a common, and I will take the global stiffness matrix, stiffness matrix of a K1, which is 12, 6, minus 12, 6, 6, 4, minus 6, 12, 2, minus 12, 6, 12, and 6. And whatever the numbers, like the elements of the matrix that are written in a red color, highlighted red color, those are the elements of the stiffness of the K2, and which are not written highlighted with a red color, those are the elements of the stiffness 1. And I want you to understand how to assemble at the common node. Since V2 and theta 2, these 2 degrees of freedom will share with both the elements, I have to add those terms. Like if I take V2 column and V2 row, the element of a stiffness matrix K1 is 12, and the element of the stiffness matrix K2 is also 12. So these two get added here. So that is the assembly. Similarly, the theta 2 of element 1 and V2 of element 2 will have a common sharing. So minus 6 plus 6. So minus 6 is from a stiffness matrix 1, plus 6 is from a element 2 stiffness matrix. So similarly, I will add the common terms V2 theta 2, theta 2 and theta 2, which is 4 and 4. So this here the addition of the stiffness matrix takes place, and rest all I'll keep as it is, because there is a no overlap of those things. V3 is not overlapping, theta 3 is not overlapping. Only the overlapping terms are this, this, this and this. So wherever V2 theta 2, V2 theta 2 are there, those are overlapped. So once this assembly is formed, I will add those and form the new assembled stiffness matrix. So upon simplification, this becomes 24, 6 minus 6, it will become minus 6 plus 6, 0, minus 6 plus 6, 0, 4 plus 4, 8. So these are the modifications, and rest all the elements remain as it is. Once the stiffness, global stiffness matrix is formed, I'll go for the nodal displacement vector, and for the nodal displacement vector I have to find the boundary conditions and substitute those values. So for that, let me go back to the model, and here I told, since it is fixed, v1 and theta 1 is 0, it is a ruler, so only v2 will be a 0, theta 2 will have some value. Here v3 is fixed, theta 3 is allowed to rotate, so V3 will not be equal to 0. So let us substitute. So from this is 0, this is 0, and this is 0. Theta is not equal to 0. V3 is 0 and theta 3 is not equal to 0. So these becomes the boundary conditions for us. So we should note this. I will be using this values in a later stage. Now similarly, I will calculate the load vector F1, M1, F2, M2, F3, M3. So that are given by these equations, these empirical equations. So already I showed how to calculate this in a previous problem. So P naught is nothing but a uniformly distributed load. Since in element 1 there is no load on the element 1, so P naught is equal to 0. So only I will have a load on a element 2. So let me go back. So in element 1 P naught is 0, so I will substitute all this as a 0. So P naught is 0. So all these terms becomes 0. Okay. Now for the element 2, it the P naught, the uniformly distributed load is acting on element 2, so I have to calculate these terms. So for that I have calculated FE2, load vector for element 2, as -6, because 12 into -12 into 1 divided by 2, so it becomes -6, minus because the load is acting downward. So similarly I have calculated for the rest of the things, and now this force vector will be substituted by these loads. So F1 M1 is equal to 0, F2 I have calculated from this, M1 M2 I have calculated from this, M3 I have calculated from this, sorry, F3 and M3. So this becomes a load vector which has a 6 parameters. So now I know what are the parameters of a displacement vector, load vector, and also the stiffness matrix. So go here, and this is the equilibrium equation. K into U is equal to F. So K, this is from the global stiffness matrix, and these are from a displacement vector. These are from the load vector. Now I will substitute the boundary conditions. We know that this is equal to 0, this is 0, this is 0, theta 2 is not equal to 0. So V3 is also 0. So I will cancel the corresponding rows. Row 1, column 1. I will cancel row 2, column 2. Row 3, column 3. So since theta 2 is not equal to 0, I won't cancel this. But V3 is 0, I will cancel this, and correspondingly that. So 1, 2, 3, 4, 5, fifth column. So I will cancel fifth column. So the leftover elements are 8, 2, 2, 4, and here theta 2, theta 3. Here -1 plus 1, and multiplied by this 800. So I will take all these values and form a new matrix as 800, 8, 2, 2, 4, and theta 2, theta 3 is equal to -1 and +1. So using this I will form a two simultaneous equation, and upon the simplification of this I'll get what is theta 2 and theta 3. So that I'm substituting here as a displacement vector. U is equal to V1 0, theta 1 0, V2 0, theta 2 from this, and V3 is 0, theta 3 is from this. So this is a nodal displacement vector. So this has to be used to form the find the maximum displacement at the center of the element 2, because in our problem is asked to find the deflection at the center of the portion of the beam carrying a UDL. So I have to find what is the deflection here. I know theta 2 and theta 3. So using a Hermite safe functions and thetas, I'll be calculating those terms. So for that, consider V is equal to H into U. So I'm not taking a V1 and theta 1 because they are already 0. So V2 is also 0. Theta 2 I have a value. V3 is also 0. So I will be using this term and this term. So V max is equal to LE by 2 H2 theta 2 plus LE by 2 H4 theta 3, where H2 is equal to 1 minus zeta plus zeta square minus zeta cube by 4, and H4 is equal to this equation. So substituting this, I know L is equal to 1 by 2, and at the center of the beam zeta is equal to 0, because if I take this, zeta is 0 at the center, and here it is plus 1 and here it is minus 1. I'm interested in calculating the deflection at the center here. So I will take theta, zeta is equal to 0. So substituting that, this all terms become 0. It becomes 1 by 4 here. So 1 by 4, and theta 2 from the load vector, this term, and theta 3, this term, I have substituted here. Theta 2, theta 3, and 1 by 2 from here, 1 by from here, minus 1 by 4, minus 1 by 4 from here. So the maximum deflection on a simplification is equal to V max is equal to minus 0.0893 into 10 raised to minus 3 meters. So that's the required deflection at the center of the second element of the beam. So let us discuss another problem. So here the load is of a different kind. So instead of a uniformly distributed load, here there is a concentrated load that is acting at the mid of the simply supported beam. So don't confuse this as a cantilever beam. So you can see here this portion is fixed in all degrees of freedom, and here there is a roller support and it tends to bend like this. So now I have to find what is the deflection at the center. So also note that here there is a no support, so the maximum deflection will be at the center. So with this, let us go for the problem, and he has given concentrated load as 10 kilonewton and length of structure is 10 meters. So I will take them as a two element. So this is as one element and this is as a another element, which is of a 5 meters of a length. And Young's modulus he has given as 200 gigapascal, and moment of inertia I is equal to 4 into 10 raised to 6 mm raised to 4. And also concentrate on a unit consistency. So since it is in kilonewton, I will convert this into kilonewton per meter square, this into meter raised to 4. So for that, So this is a discretization of the element, like I have considered it as a two element of a 5-meter length. So in the sense there are 6 degrees of freedom, 2 on each node, v1 theta 1, v2 theta 2, v3 theta 3, and 6 load vectors f1 m1, f2 m2, f3 m3. So already we have discussed this in the previous problems. So once we have idealized the FE structure, let us go for a equilibrium equation. This is shown for a one element. So I will be using this stiffness matrix formula to calculate the beam stiffness of each element. So for calculating EI by L cube, so after unit conversion, it comes to a 6.4. So I just have substituted wherever L is there, it has to be replaced with a 5 meter. So let us go for the element stiffness matrix, that is K1 for element 1. So K1 is equal to substitute 5 wherever L1 is there. So upon the simplification, I'll get this stiffness matrix, and note that V1 theta 1, V2 theta 2, V1 theta 1, V2 theta 2. Don't forget to uh, represent the rows and columns with the degrees of freedom. Similarly, for a K2, V2 theta 2, V3 theta 3, V2 theta 2, V3 theta 3, and here L2 is 5, and substitute wherever L2 is there, substitute with the 5 meters, and this constant is same 6.4, and the rows and column representation with the degrees of freedom is done. So once the stiffness 1 and stiffness 2 is formed, I have to assemble it. So for assembly, just I will show it. So kg is equal to, so 6.4 as it is outside, and here I have to form 6 by 6 matrix, v1 theta 1, v2 theta 2, v3 theta 3, and corresponding rows v1 theta 1, v2 theta 2, v3 theta 3. So I will arrange. So you have to concentrate on adding of these terms. So there will be a one element from K1 and one element from K2, and one element for this theta 2 and V2 from K1 and K2, and here the addition of the matrix takes place. So that is shown in the next slide, like Kg is equal to K1 plus K2, and these terms are added. So already I have shown this in the previous problem. So I hope you have followed this. So rest all elements will be same as it is. So this becomes 24, and this becomes, I think it has to be positive here. I missed it here. This becomes 0, and this becomes 0. This becomes a 200. So upon simplification, yes. So these are the changes, and rest all elements remain as it is. So once the global stiffness is formed, apply the boundary conditions. So for applying of a boundary conditions, already we know that. So let us go back to the diagram. So it is fixed here in the sense v1 equal to 0, theta 1 is equal to 0. So here v1 equal to 0, theta 1 equal to 0, and since there is no support, we don't know what is the value here. And also V3 is equal to 0 because there is a support there, but there is a roller support, this won't be 0. So these will be the unknown terms, V2, theta 2 and theta 3. So this becomes a load vector, and this load vector will have a different empirical formula for the concentrated load. So it is P naught by 2. So there is no concentrated load at node 1, so it becomes 0 0, and but here it becomes a P naught by 2 because at a node 2 there is a 10 kilonewton, so that is 5, so it will be a minus 5. And similarly this sorry, it has to be minus 5 0 0 0, so this won't be there, so it will be minus 5. So upon the simplification, this 5 and this 5 adds up and V2 will becomes a minus 10. So now the load vector will be 0 0 and V2 is minus 10. Theta 2, oh no, sorry, M2 is 0, uh, F3 is 0 and M3 is 0. So this load vector is from the diagram here. Only the load is acting at the center, so which is at a V2. So these terms will be 0. Force at node 1 and node 3 will be 0. Moment at node 1 and node 3 will be a 0. So upon simplification, so I will cancel this row, the corresponding columns. V2 I don't know, I should not cancel it. uh, Theta 2 I don't know, so I should not cancel this. V3 is 0, so cancel it. So this is the fifth column, I will cancel this. So the leftover terms are these terms and these terms, and here these and this, these and this, and 6.4. So I'll take all these parameters and form a new matrix as this. So using a matrix, above matrix, I can find the inverse of this and calculate V2, theta 2 and theta 3. You can use a calculator for calculating this V2, theta 2 and theta 3. So upon simplification, I'll be getting what is the displacement at a node 2, that is V2 is equal to minus 0.1139 meters. Theta 2 is minus 9.7656 into 10 raised to minus 3 radians. Theta 3 at node 3 is 0.03906 radians. So with this, we complete problems, 3 problems on the beam. So you can solve some more problems using the same methodology. Thank you.